Okay. Okay, so welcome everyone. So for the past 3 lectures, basically what we've been doing is that, of course, we've been doing implementing constraints on our S matrix and deriving, like using these constraints to uniquely fix things. And so for example, if we consider the scattering of 4 gravitons, through our exercise of fixing the 3-point and factorization pole, and we can fix our answer to this form. This is, and as I mentioned, this is the usual Einstein gravity, the 4-point amplitude of Einstein gravity. Many of you have been asking, so can I say anything about things beyond this? So of course, when I write down my amplitude, I will have the part that has factorization poles, have singularities. But then in principle, there's nothing wrong with me writing down all of these terms, right? I can just write polynomial terms, just keep writing them and writing them and writing them. And here, this is relatively constrained because I'm scattering 4 gravitons, so it has to have permutation invariance. So when I write down these terms, they're all manifestly permutation invariant. So for example, you have S plus T plus U. Of course, this is 0 for those who are paying attention. This term is actually not there. But you can write all of these terms, and for example, at the 6th derivative or 6th Mandelstam variable, degree 6, so you actually have 2 different terms, but you can write infinite number of them. So first of all, what do these terms correspond to? If you try to write down an action, the Lagrangian, as usual, we would write down minus square root GR, and this will give you this amplitude. So the fact that you can write the amplitude, you can write down infinite many terms that look like this, just corresponds to that in the action. You can start to add a Riemann tensor. I'm just going to use R, for example, some D to some power N and R to, for example, these are all arising from operators that look like dn r to the 4. Okay, that gives these terms. So the fact that your amplitude is not fixed at all beyond the leading term is actually reflected in the fact that your Lagrangian, you can just write down arbitrary these terms and these what we call higher dimension operators, and you have this degree of freedom of writing them, right? And through Marcus's talk, you know that the fact that you have these higher dimension operator is a reflection that you have another UV theory. And there's some UV theory with some cutoff at high energy, and because you're only looking at things in low energy, and therefore you have these infinite number of these terms here, these higher dimension operators, and this is, in a sense, an effective field theory description of this. And the coefficients associated with these terms, in some sense, parameterize your high energy, the high energy theory, right? So today in this talk, what we're going to try to do is is there something you can say about these coefficients or about these operators just from consistency of your scattering amplitude without ever even knowing about what exactly is the high energy theory. So that's what we're going to try to do today, okay? But before trying to do that, I'm just going to play a little game, and let's just try to construct. Can we just, on the blackboard, let's just try to construct something that can be viewed as the UV completion of gravity. Okay, so we're going to complete gravity on the blackboard today. Okay, and so how are we going to do that? Well, we're going. I mean, as you see in Marcus's talk, generically in the ultraviolet, you would have new states, and so for example, you might have new degrees of freedom propagating. So we just use that information. So first of all, so that means that since I have new states propagating, so let's say I have a state. Whatever the mass is, I'm going to normalize it to 1. It doesn't matter. It's just some scale. I can normalize it to 1. So then that will mean that I have a state, and so I need to modify my S matrix. So this is the original tree level part. And I modify my S matrix by adding these massive poles. You might say, hey, but shouldn't it be like a massive pole in an S channel plus a massive pole in a T channel plus a massive pole in a U channel? Why am I putting everything together? Well, because I can just put them together, right? And whatever, and you just Mathematica together, and it'll throw you some numerators in front on top, right? I can always do that. So this is a very general formula, right? Now you might think that I can just do whatever I do here, but no, we have some, we need to do things that actually make sense. For one, first of all, since we're UV completing this, so what it actually means by UV completing is, as I'll go into a little bit more precise later on, we want this to have a better high energy, we want this new thing, this UV theory, to have a better high energy behavior than just the low energy effective field theory, right? And most of you know that if I was just looking at gravity here, all of these are momentum powers, so you can see that there's 8 momentum powers, there's 6 momentum powers downstairs. So that tells you that gravity, this amplitude actually grows as E squared, and therefore it will diverge and high energy. So at the very least, what I want to do is I want to tame this E squared. Okay, I want to make this high energy behavior slightly better than E squared. Just better. I don't ask a lot. I just want to be slightly better than E squared. Otherwise, what's the point of doing a UV completion? So if you look at this, and if you wanted to have, so first of all, I want to have better UV. I want to have better UV. Then this immediately tells you that NST, by the way, I just write it as a function of S and T and no U. Can anyone tell me why? Yeah, okay, just making sure everybody had their coffee. Okay, so as NST can only be degree at most 2 in S or T, right? Because this is already degree 3. So if I have degree 3 or beyond, beyond is going to be worse than what I had before, right? If it's 3, then I'm not really improving anything. So I want to have degree 2. So that already tells you don't have much degrees of freedom, because that tells you that you can only write NST to be S squared. This is just an overall normalizing factor, so I don't need to put a coefficient here, plus AST plus BT squared. This is the only thing you can put up there if you want to improve things. Okay, so you say, okay, but that's great. We have 2 parameter families of solutions that can make that thing better, right? What? Oh, sorry. Yes. Oh, sorry. What am I doing? Yeah. And then I have the linear terms, the CS plus DT, and then plus the constant. Sorry, I should have completed this. Yeah. So this is the general thing I can have. Very good. However, now you have these massive poles. As you know, that whenever we have a rational term where we have poles, and that you must talk about the residue of that pole. What happens when the denominator becomes 0, right? When the denominator becomes 0, that means you're going on shell. When you're going on shell, that means that, for example, if you're sitting on S equal to 1, that means that you're supposed to be producing some massive particle where the mass is 1, right? The residue of that, again, as we know, should be, so when S equals to 1, the amplitude, or the 4-point amplitude, should behave as S times 1. So there's a pole here. And here it should be the product of 2 3-points. Right? So there's a non-trivial constraint here. It needs to be a product of 2 3-points. What is it? So since we've been fixing our 3-point amplitude, and we know that our 3-point amplitude are just these momentum or spinor bracket things multiplied to each other. So that means that this guy on the numerator has to be a polynomial. Right? This has to be a polynomial. Right? Said another way, the residue of this guy at S equals to 1 has to be a polynomial. But as you can see, it's not so easy for it to be a polynomial, right? So when S is equal to 1, the residue of this at S equal to 1 equals to what? So I just plug S equal to 1. So this is N1T. However, you still have these poles down here. You have this T minus 1 pole. U is equal to minus S minus T. S is 1, so this becomes minus T minus 2. And S is equal to 1, there's no problem. I have a T here. And then I have U equals to minus S minus T. And this is minus 1 minus T. Okay, and then I have the spinor bracket here. This is some awful looking residue. Okay, this is some awful looking residue. This is not at all polynomial. Okay? Now, so that means that you want to fix this numerator such that the numerator, so then the numerator put s equal to 1 here, you need to fix it such that all of the denominator gets canceled out, right? Or said in another way, the numerator needs to have zeros and t at the same positions where your numerator or denominator have opposed in order for this to be a polynomial, right? But now you see the problem. T is at most degree 2. I have 1, 2, 3, 4 poles in the denominator, right? And so it's impossible. There's no solution to this problem. Okay, so this simple exercise, I have no solution. Okay? What about, how about I just have another guy? So let's say this was, originally this was M1. So you might say that this, how about I have 2 states, M2, sorry, this is M squared, and then I have another state, S minus M, let me say prime squared, T minus, if I just add another state, because of the fact that I have another state, therefore my denominator becomes bigger, and that will allow me to boost the degree of T numerator higher, right? Previously, the denominator just has 3, so that's why my T polynomial here is just degree 2. If my denominator has degree 6, now my T can be of degree 5, right? So I can boost my T, right? But as you might imagine, now I'm actually making things worse, right? Because now when I'm sitting at a pole here, I need to cancel this guy, this guy, this guy, this guy, this guy, and of course the guy in front, right? And just thinking about this, you realize immediately that if I try to play this game, there's never, any new states that I add is just going to make things worse and worse. Right? This mismatch between the fact that there's a tension here, the fact that this needs to have the same zeros as where this have poles, there's a mismatch between zeros and poles for generic mass, right? So it's actually not so trivial. Even so, I'm just imposing just 2 conditions. I'm just imposing, first, I'm trying to augment this function by the fact that I'm adding new particles. And I want to add it in such a way that I'm actually, I don't want to like completely solve the problem, but just make it slightly better. But then the fact that on the residues, this should always be considered as this picture where you have this factorization, immediately tells you this looks like there's no solution. Unless there's something funny about these mass positions such that the same zero can be used more than once. Okay? And if you slightly think about it, you'll realize that there's actually a very simple solution to this problem. And that is, so let me write it down. There's a very simple problem solution. And that is that the mass are all integer, or integer are all integer to a particular scale. So they're all integer space. Why is integer space good? Because, for example, if let's say s is equal to m squared is equal to 1, and this, so that means that this has 1, or let's say when you go higher, when s equals to 2, then 2 can be split into multiple ways. So the same thing can be actually used to cancel different number of poles. So that tells you that there's actually a very nice solution to this problem. And it's just very simple. So this is just 1 to infinity. And this is just 1 to infinity. This is just, so this is all the poles, t plus I, sorry, s minus I, t minus I, u minus I. And this is all the zeros, s plus I, t plus I, u plus I. Okay, so what am I doing here? I'm making it manifest that whenever s is sitting at a particular pole, let's say s is sitting at 4, you plug 4 into here. Here, you have sufficient number of zeros. There's always some zeros here that can cancel the pole that you have down here. So this is a solution which manifests this requirement here, that the residue will always be polynomial. Okay, you can what? No, that's not the only solution, but this is like the easiest one you can guess. So this is so this solution is a solution where you manifest this property. So for example, s equal to 4, if s is equal to 4, then this is just 4. Then this has 0 at all integer values. And since this has 0 at all integer value, this can exactly cancel the poles downstairs. So right now, you say that I have infinite number, but first of all, this infinite number is not making things worse, right? Because they're match, right? They're match. And since it's infinite, so that actually means that its high energy behavior is not read off just from this, right? Because this is you need to continue this in the correct fashion. But this at least has a chance of solving this problem. Or this definitely solves this problem, and it has a chance of improving the high energy behavior. And as most of you know what I'm getting at, this is exactly string theory. Okay, this answer is precisely equal to, so this is, if you look at your gamma function, this is precisely, so this I can write it as, I can put STU and combine it up there, and this, you can write it as 3, 4, and this is just gamma minus S, gamma minus T, gamma minus U, over gamma 1 plus S, gamma 1 plus T, gamma 1 plus U. Okay? So this is your type 2 string graviton scattering amplitude. And you see that this answer just drops out if you just try to treat this as an amplitude and try to solve it in the dumbest possible way, just requiring that at any point, every new UV physics that you add in is always local in the sense that when I'm sitting on any of these factorization poles, when I'm producing this UV state, the residue is always a product of 2 3-points, as where the 3-point is something that we've been doing before. And it turns out this is the first simplest answer that you can have, that you can write down. Okay? So this is a UV completion. But in fact, we can still do, let's say I have this answer. Since what I want to do is I want to do consistency conditions on, and use this consistency condition to constrain what these Wilson coefficients of these higher dimension operators can be. Therefore, I will use this amplitude to tell you what kind of constraints you can put on the UV. Okay? So one is already, you know, that on the pole, that it factorizes into the 2 3-points. Okay? Now let's look at this 2 3-points. So let's treat it as a scalar. Since this is just a prefactor, I can remove the spinner part. Then this would be, oh, okay, now I should change shoes. Okay, so you can treat this as a scalar amplitude. So what are the residue of your scalar amplitude? So the residue would be something that looks like this. So you have, so these are scalars, and then you have some intermediate state, and then you have 2 scalars coming out, let's say. Now this state will have to form irreducible representation under your little group. Depends on what your dimension is. So let me call this a spin L state. And this is a spin L state coming over to a spin L state, okay? It turns out that this 3-point amplitude is actually extremely simple to write down. This thing is just equal to, if I call this 1, 2, 3, 4, then this thing is just P1 minus P2 mu, let me call it mu1, P1 minus P2 mu2, all the way to P1 minus P2 mu L. And then I'm going to use polarization tensor for now. The reason that I don't use spinor helicity is because right now I want to just do this for any dimension. I'm not going to restrict myself to 4 dimensions. So this will be the amplitude that you have for a spin L on this side. So you see that this is unique for a very simple reason. So first of all, the fact that you have a spin L state here means that you need a rank L, sorry, a rank L tensor, a polarization tensor. So you need a bunch of vectors to dot into this, right? The vectors, the independent vector that you have in this problem is just the momentum 1, momentum 2. Momentum 3 is related to momentum 1 and momentum 2 by momentum conservation. You just have 2 momentum, right? And if you have 2 momentum, there's really 2 vectors. You can have P1 minus P2 or P1 plus P2, right? This is the only thing. And since P1 plus P2 is basically just this internal momentum, P1 plus P2 dotted into your polarization tensor is just 0 because this is transverse, right? So that means the only vector that you can have in this problem to dot into your polarization tensor is just P1 minus P2. Okay, so this amplitude is unique. This is the unique amplitude you can have on this side. And so the same thing is a unique amplitude that you can have on the other side, where you just interchange P1 minus P2 into P3 minus P4. Okay? So if you have this is your unique amplitude, and then you plug it into here, then, so this, let me call this A3 left, which depends on epsilon left, or this is A3 left contracted with a spin-L state. Then, of course, I have A3 right contracted with this spin-L state, with this spin-L internal state. And then my residue for this, so the residue for this factorization is just A3 left with this spin-L polarization and A3 right with this spin-L polarization. And then I just sum over all the different kinds of polarization that you can have, right? What do we mean by all the different kinds? Because this polarization vector needs to satisfy transverse condition, and so there's multiple solutions to it. And you just need to sum over all multiple solutions, okay? So that corresponds to summing over all the possible intermediate states, okay? If you do this, there's a very easy way to see what you're going to get. So let me just use 1 minute to do this. So let me call this vector x, and P3 minus P4, and let me call it y. Let me call this, define this as a y vector. So this is essentially summing over your polarization. So this will be a bunch of x all the way times your polarization vector, and then there's another bunch of y multiply your polarization vector. So as you can imagine, once you sum over all of your polarization vector, you're just going to get inner products between x and y, right? Of course, because this is irreducible representation, so you need to take out the trace part of this. So this is symmetric traceless. So that means that you're going to get a function, let me call this fxy, okay, where this function satisfies box x equal to 0, right? Because box x means that I'm contracting 2 of them, where 2 of them just means I'm taking a trace here. And since this polarization vector is 0, so that means that I just need to solve this function. Of course, this is not exactly 0, because of course, if x and y are the same, then they don't need to be 0 anymore, right? Because then you can have this box x acting on here, one derivative acting on here, and since x and y is the same, another one can act on y. So you know that this really is just a d-dimension x minus y. Okay, so this residue is related to the solution of this equation, which is nothing but your Green's function, right? You already solved this before. And so you know that the solution to this, so the solution to this is just, in general dimensions, is just x squared minus 2x dot y, or sorry, let me just write it, x minus y squared. In general dimension, this was a d minus 3 divided by 2. So you can see that in 4 dimension, it just goes to the usual 1 over x minus y, the solution to the 4-dimension Green's function, okay? So if I write this out, then this will be x squared minus 2x dot y plus y squared d minus 3 over 2. So x dot y, so x minus y, so x is here, y is here, so you can see that x dot y essentially gives you the scattering angle of this process, okay? Because if you're in the center of mass frame, then the scattering angle is defined as P1, P2, P3, P4. And this is your scattering angle. Okay? So if you plot this configuration here and you do a normalization, you'll see that this is nothing but 1 minus 2 cosine theta times, let me just call the scale of y to be r, plus r squared d minus 3 over 2. Okay? And of course, if I have, so this is for any spin L will satisfy this equation. So in order to pick out the particular spin L, I just need to expand this and pick out the r equals L, the degree L part of my r. So if I write this expanded out, I can write this as sum L equal to 0, infinity, r to the Lth power, and then this will give me some function of cosine theta. And this will depend on my dimension d, and this will be dimension L. So I can expand this out. So for those of you who still remember your applied math, you know that this is, when d equals 4, this is the generating function of your Legendre polynomial, right? And for generic dimension, this will be the generating function of what is called the Geigenbauer polynomial. So these are the generating functions of the orthogonal polynomials, okay? So that tells you, so what is this, so what I'm doing all this, what I'm trying to say? What I'm trying to say is that the residue, since it's a product of two identical 3-point amplitudes of spin L, that means that the residue, here, let me just make it more precise. So the residue at S equal to n, or any mass, has to be equal to, you can always write it as a sum of this Geigenbauer polynomial. Importantly, with, so this is L equals 0 to infinity, but very importantly, this LD is bigger than 0. This is always positive. Okay, this is very important. Why is it always positive? Because it's a product of two identical 3-point amplitude, right? So whatever the coefficient that you have in front of here is, if you have the coupling constant for your 3-point amplitude, then it's the square of your coupling constant, right? So that means that this should be always positive. This is a very non-trivial constraint on this function here. Okay, so now what I need to do is, in order for this function to actually make sense physically, I need to sit on every one of these poles. I take the residue, I put it into my scattering angle. So the relation between your kinematic invariance and your scattering angle is, so many of you should be familiar with this, is that t equals to minus s over 2, 1 minus cos theta. So you can always replace, and u is going to be minus s over 2, 1 plus cos theta, where again, this theta is the scattering angle here. So when you sit on the residue here, and you get a function of your scattering angle, you expand on this orthogonal polynomial basis. It better be that each of these coefficients has to be positive in order for this to make sense. Okay? So this is the crucial constraint that we're going to use. So this is what is called the positivity constraint. And of course, there's various ways to derive this. But this is what we're going to use. And so now let's exactly use it on that amplitude. In fact, oh, sorry, I should keep this. You could have done the same thing with gluon amplitudes. And if you do the gluon amplitudes, then you would get exactly a similar argument, except that now because you only have ST, sorry, this is gluons or vectors, then since you only have S and T channel poles, so the answer you will get looks something like this. So we have two sets. So this is also what is known as the type 1 open string amplitude, but you also get the same derivation. You get the same result just using my previous argument. So, okay, good. So now let's just test this. So I'm going to test this on my computer. So just to show you viscerally how this works. So let's just wait minutes for this to come out. So just to let you know precisely what I'm going to do. Okay, good. So you see my Mathematica notebook. All right, so let's first use this open string guy here. And is it big enough for everyone? Yeah? Okay, good. So this open string amplitude, I have gamma minus s, gamma minus t over gamma 1 plus u. Okay, so first I do momentum conservation. I set u equals to minus s minus t. So, and then I use this formula where t is minus s over 2, 1 minus cos theta. So I do this replacement. So here cos theta is x. Good. So now let's look at the residue. Okay, so now first I look at the s equal to 1 residue. Oops, that's Chinese. Change it. So I just use s equal to 1. Okay, so the first level is just a massive scalar because it's just a constant. So that means it's changing a scalar. Okay, so there's nothing there. The residue is positive, perfect, no problem. Now let's look at the second level. The second level is x over 2. It's just cos theta over 2. It's again positive, so it's exchanging a positive spin 1, no problem. Now let's look at residue 3. Interesting. So now at the third residue, my polynomial is 9 times cos squared theta minus 1, or I can just pull this out, minus cos theta minus 1/9. Now, that means, because this has a cos theta square, so that means you're exchanging a spin 2, right? There's a spin 2 in your exchange. But it can be a spin 2 and then spin 0 with a different combination, depending on my space-time dimension. So let me just use Mathematica. It's very good. It already encodes the Gegenbauer polynomial. So let me call out my Gegenbauer polynomial, and let me look at its form. So if I have a spin 2, the first entry is spin 2. The second entry will be d minus 3 divided by 2. So let's say we go 6 dimensions. So d minus 3 over 2 will be 3 over 2, and then x. So the Mathematica tells me that this function looks like. So in 6 dimension, if this was a 6 dimension theory that is being exchanged, then the spin 2 will be cos theta minus 1/5. Is it 1/5 actually? Yeah, it's minus 1/5. Okay, but now my residue is cos theta minus 1/9, right? But that's no problem because it can be minus 1/5 plus a positive constant to make it 1/9, right? So this will be 1/5 minus 1/9, right? So that means that this residue that I just looked at in 6 dimension looks like a spin 2 times 1 plus this constant times spin 0, right? So no problem. It's unitary. It's positive. It's perfectly fine in 6 dimension. I guess you know what I'm going to do. I'm going to boost the dimension up. So I can boost my dimension up. So let me just boost it two dimensions up. So this will be 5. And now it's minus 1/7. So this becomes minus 1/7. This becomes 1/7. This is still positive because 1/7 is bigger than 1/9, right? Okay? But you see what's going to happen, right? As I go to dimension higher and higher, eventually this constant piece is going to go negative, which tells you, hey, this amplitude has a critical dimension. When it goes beyond that critical dimension, this amplitude no longer makes sense. And I guess you can guess what that critical dimension is, right? So you see that if I plug in 10 dimension, then d minus 3 is 7, exactly the 1/9. Okay, so at 10 dimension, now this becomes 1/9. So at 10 dimension, this scalar drops out. You just have this spin 2. It's still unitary, and therefore it tells you that at 11 dimension, this ceases to be unitary. Okay, so from this analysis, we guess the answer, and we actually learn a lot about this theory. This theory can only exist in 10 dimensions and lower. There's actually a critical dimension in this theory. Okay, and what is the constraint that we're using? The constraint that we're using is that whenever I'm sitting on this kind of factorization pole, this has to be a positive expanded on my Gegenbauer. So you can see that how strong this constraint is. Imposing this constraint, we have no picture of worldsheet, we don't know anything about quantization, nothing, we're just guessing some random answer out that satisfies these very simple constraints. And I find that I have an answer that looks nice, and this answer lives in 10 dimensions, okay, without even ever going through a worldsheet picture. Okay, so you can see how strong this constraint is. So now, so I was just using this as a toy toy model to see how strong this constraint is. Now I want to forget about this and just go back to using that constraint and look at what does it say for my low energy theory, okay? But even before doing that, there's actually much more you can do. So this is just about the positivity expansion of your kinematics. You might think that, hey, I want to talk about group theory. I want to talk about global symmetries. You can imagine that you're scattering, instead of these gravitons, you're scattering states which carry global indices. You can do exactly the same analysis. So let me just give you a very simple example. So you can also use it. You can also use this to see. Let me just. Okay. Okay. So for example, now let me instead say I'm scattering four adjoint scalars carrying some adjoint group. Okay. And again, I do this exactly at the same analysis at low energy. This adjoint, at low energy, I guess there's no pointer. You can see my, is there a pointer here? Oh, here, good. Okay, it's good. So this is exactly the same thing. At low energy, I have your usual, so this is your Yang-Mills amplitude at low energy. You have ST, TU, SU. And then and you also, because we're in a gravitational world, so there's also the gluons can exchange a gravitational pole. Again, I want to UV complete this. Using the same argument that I did here, a natural UV completion will be just this low energy amplitude multiplied by the stringy function that you have here, okay? Now I can do exactly the same game I just did before. I sit on my residue. Now, but because that now I'm scattering global states with global symmetry state, so the residue is expanded on two things. The kinematic part is my Gegenbauer polynomial, which I just introduced. But then because you have these global indices, so there's also a polynomial or what we call projectors, which you should put here. What is this projectors? Well, this projector just reflects all the possible different irreducible representation of your SON. So it should be expandable on that projector. Okay, I mean, if you want to see what it looks like, the projector, you can, so there's, for SON, this is an XON thing. So the projector, so for example, you have the one, this will be just a singlet, meaning that internal thing doesn't have any global indices. But then depending on the internal, this is like a double line notation, you can draw it out. So this is the 6 independent irreducible representation that can be exchanged. And therefore, you just expand it out on the projector, and then you require that this is positive. If you do that on that function, so I have 6 projectors, so these are the residue of my 6 projector for a level, at level 1 of that function. And so the constraint is that every one of these has to be positive. And obviously, for SON, n has to be bigger than 2. These are all manifestly positive. The only thing that is not manifestly positive is these 2 functions. So if you require that these 2 functions are positive, you immediately find that there's no solution beyond 35. Okay, so this is another. So you immediately see that your gauge group is bounded. Or yes. So this alpha is parameterizing your representation. So alpha goes from 1 to 6, depending on which representation of your global symmetry is. Which irreducible representation of this exchange is under your SON transformation. Yeah, it only goes, there's only 6 independent of them. And so this is something more finesse than what I just said. So previously I was just talking about kinematics, and that imposed constraint on your space-time dimension. Now I'm also imposing group theory structure in terms of representation theory. And you see immediately that also this imposes strong constraint. This immediately gives you, we were not doing any anomaly cancellation, nothing. This just tells you that coupling to gravity in this way of UV completion actually puts bounds on the rank of your gauge group. Of course, this is just doing level 1. I can do level 2, level 3, level 4, and then you get a picture that looks like this, where you have, of course, the bound is also is related to the ratio between your Yang-Mills coupling and G string, but you see that there's a sharp cutoff in the allow region of your gauge group, and the string theory answer, SO32, for example, sits exactly at this corner here of the allowed space, okay? So this kind of plot is going to be the kind of plots that you will see in the remaining of the talks, which is I'm going to try to impose the consistency condition on some kind of parameterization, and what are the allowed space of that parameterization, of what is the space that these consistency condition allow, okay? Good. Of course, you should not take this too serious, because I'm essentially assuming the string theory completion. I don't have to, as Joanna asked, I mean, this is not the unique solution at all, far from it, okay? Even within string theory, there's multiple solutions. So but I just want to use this solution to let you see how powerful these constraints are. And now what I'm going to do is I'm going to now go into a more general approach of how I can harness this kind of constraint. Okay, and so to harness this constraint, what we usually do, and this then falls into what we usually call the S matrix or the effective field theory bootstrap. And the idea is that my amplitude, or my 4-point amplitude at low energies will have this structure here. So first, it will have terms that reflect the fact that it has massless poles. And then it will have terms that have a polynomial expansion. So now I'm calling this G, K, Q. So these are the coupling constant. S is K minus Q. T is Q. Of course, I sum over all possible KQ with the condition that Q is always smaller or equal to K. Okay, so at low energy, I have this form of my amplitude. And sorry, one second. And this form, these GKQs are precisely mapped 1-to-1 to your Wilson coefficients linearly of your effective field theory. Okay, and so we know that low energy, our amplitude looks, this is how our world looks like, right? And now I want to say, can I say something about these coefficients? Okay, so yes, what is the question?
The question is that if with other solutions for the function, do we find always the same constraints, or at least compatible ones?
You mean if we have other solutions, can we apply the same constraints? Is that the question?
Yeah, I mean, because we parameterize our function eta, was the name, with the poles and.
Yeah, but really the point is that this is a function of S and T, right? This is a function of S and T with poles. So whatever you put here, I can always sit on this pole and then I immediately do this analysis. So
but
actually,
then the constraints are always the same?
Yeah, there's always the same. This constraint is the physics constraint.
Okay.
So how's that? Right, and some of you might know that recently there's been a lot of people trying to propose new function solutions that are inspired by string theory. And these solutions that they put out are precisely solutions that satisfy these constraints that were later ruled out by other conditions. Some of them are ruled out, some are still surviving at the moment. And I'll talk about what are the other things that you can impose on this. But right now I'm just going to impose this constraint and see what we can do.
Different constraints, right? I mean, if we consider another solution, there could be another different constraint for the dimension or for the X, right?
Oh, yeah, for sure. No, well, what I mean by constraint is just that you're imposing that it has a positive expansion on these Geigenbauer polynomials. That's what I mean by constraint. Of course, the solution to the constraint might be different.
I was asking about that.
The solution.
If you find that the dimension can be greater than for example.
Oh, okay. So I guess what you're asking is that if I look at one pole and then I have do this analysis, my dimension is 10, and I look at another pole, I look it's 24,
Yeah.
and of course then 10 it wins, right? Because if you have
Okay, the
one
most
residue that only
restrictive.
violates at 25 and one that violates above 10, then of course that tells you that the dimension is 10. If you have some other pole which shows you that the critical dimension is 6, then 6 wins. Okay, it's which constraint is the strongest?
Okay,
Yeah, because, yeah.
thank you.
But adding on to that, maybe if I have two different solutions, and in one solution I get the constraint is critical dimension is 8, in another solution I get critical dimension is 9, then how do we decide, or they're just completely different? Does it place constraint that critical dimension must be 9?
Well, you have two different solutions, then that's two different theories. One
different
theory
theories.
has a different critical
So
dimension.
they're just completely distinct.
Yeah,
Okay.
yeah. Okay, very good. So we know that our low energy amplitude looks like this, okay? Now, let's say we have the full UV completion, F at A4ST, okay? Now, what is the analytic behavior? So now I'm going to talk a little bit about what is the analytic behavior that I expect for this 4-point function. So I'm going to view this as a function. So I'm going to consider at fixed t, so t equals t star, where t star, or the absolute value of t star, is I hold it below my cutoff, or below my UV theory, or whatever the cutoff scale that you have. Okay, so t is, so for example, you can take t equals 0, then you don't even care what the cutoff scale is. Okay, so, but you can play around, well, we're going to play around with small t, but the t is just tiny, whereas it's compared to the cutoff. Okay, so if we consider this, then then A4ST star is basically a function of S, and we can talk about the analytic property of this function S on the complex S plane. On the complex S plane, how does this function actually look like? On the complex S plane, because t is very small, but lower than all the UV physics, so you can argue that the only where there's something non-trivial going on is when the S channel is exciting the UV physics that generates these massive on-shell states, right? So that means that you can, starting from m squared, you can have poles or you can have branch cuts depending on how the UV states come in. It can come in the S channel, but it can also come in the U channel. Okay, so the U is negative S because U equals negative S minus T. So they can come in U channel, and then there's some, you can have poles or discontinuity. Again, starting at minus m squared minus T. Okay, sorry, minus T star. Okay. But importantly, everywhere here is analytic. There should be nothing going on everywhere here. Okay, because of the fact that I'm controlling my T star to be, let me just let it, just to be super safe, to be smaller than my UV physics. Okay, good. So this is input 1. So my analytic behavior of my function, and of course, there's a massless pole as S goes to 0. There's some non-trivial things going on here because I know that at low energy, this is the form of my answer at low energies. Very good. Now I can consider doing an integral. Okay, let's consider doing a contour integral here. So let me consider doing ds over some s to the n power ast star. And let me just consider doing this contour integral, where the contour goes through infinity. Okay, it's encircling infinity. Okay. Now this equation, the value of this equation appears to rely on how this function behaves at infinity, right? But as you can imagine, since I'm weighting it by n here, I'm weighting it by n here. If my function is bounded at infinity, then for sufficient power of n, this is going to be 0. I'm going to determine what that n value is. Right? Okay? As for sufficient value at n, if it's bounded, if it's polynomial bounded, then this contour integral is just going to give you 0. If it gives you 0, then I'm super happy, because that means that since this contour is 0, that means that because there's pose and branch cut, that discontinuity, the non-analyticity on the UV state is going to give you information about what's happening at the origin. Why do we say that we're going to pick up things at origin? Because you have this ds to Sn, so there's going to be pose coming from s equal to 0. So if this integral goes to 0, then this tells you that you have a immediate mathematical equation that relates the UV physics, the discontinuity which is related to the UV, to whatever you're picking out your IR couplings here. If you know what value of n is that allows this to be 0. Okay? Now, what is the value of n? Well, I will argue that the value of n has to be greater or equal to 3. Okay? If n is greater than or equal to 3, I can safely say that this integral is going to vanish. So how am I going to argue it? Of course, I'm going to be super hand-waving about it. But there's been really a lot of work recently to try to establish what exactly is the correct power of n here. So this is related. So first of all, let's go to a very cartoon picture. And that cartoon picture is, let's say we have some scattering of two objects. And of course, the interacting is mediated by some force. Let's first assume that the interaction is mediated by something that has mass m. So if the interaction is mediated by something that has mass m, which this is usual statement that it has a gap, then you know that the two-point function has an exponential minus mr decay, right? For the two-point for example, a Yukawa coupling that exchanges mass m. So that means that your amplitude should be proportional to something that looks like g. So this is a coupling constant, depending on the center of mass energy, to some power. I don't care what that power. But in the what we call the impact or impact parameter space, this has the exponential mr suppression. And so therefore, this tells you that this interaction strength is only relevant when the separation of these two particles, or in the impact parameter direction, is r smaller or equal to n times log e over m. Okay, only for r smaller than this region is there really a sizable interaction. For r bigger than this region, because of this exponential suppression, then there's really no sizable interaction at all, or or things will shut off. Therefore, that tells you that your cross section, which is supposed to be proportional to your r square, has to be bounded by n squared log e squared over m squared. Okay? And finally, since from the optical theorem, you know that the total cross-section is going to be proportional to the imaginary part of your amplitude, the forward amplitude, or divided by s. This, combined with this hand-waving argument, you see that this tells you that the cross-section must be bounded by s log s, as s goes to infinity. Okay? Or I can replace this by the imaginary part of my forward amplitude. Sorry, my forward amplitude is bounded. Sorry, it's the imaginary part, yeah, so my imaginary part is bounded by s log s. Okay, so first of all, since it's bounded by s log s, so that already tells you that this function should be bounded as s goes to infinity. And it's actually bounded by a polynomial that's relatively low degree. Okay? Now you can further show that if you remember that if you do the partial wave expansion, you can show that actually So if we do the partial wave expansion, since my amplitude, so if my 4-point amplitude expanded on partial waves, I can write it as L goes to 0 to infinity, AL times FL, so AL will be a function of S, FL d cos theta. So the imaginary part of my A4 is going to be equal, of course, the same thing, but with the imaginary part of my AL. Okay? But at the same time, you know that the forward limit, A4 st equals 0, which means that this cosine theta is set to 1. This is equal to the total cross-section. This is equal to the total cross-section. Sorry, this square is equal to the total cross-section. It's also, sorry, the elastic part of the total cross-section. The imaginary part will be, the forward limit will be the total cross-section. Therefore, you can, from this, you can deduce that your imaginary part is actually going to be bigger than just the absolute value AL squared. Okay? Since I'm already bounding my imaginary part, therefore my total amplitude is actually bounded. Okay? Just from this very fast argument. And therefore, I conclude that, from this analysis, I conclude that my AST in the near forward limit, in the limit where T star is going to 0, in the near forward limit, divided by S squared, is going to be equal to 0 as S goes to infinity. So it's bounded by S squared. Okay, so this is the what is famous called the Froissart bound, but of course it uses more partial wave expansion analysis than what I've just talked about here. But this is basically the spirit. Okay, so that means that as long as, since this bounded by S squared goes to 0, so that means that this is behaving at S squared. So as long as n equals to 3 or beyond, this contour integral is going to be 0. Now, of course, you might say that, hey, I'm using an assumption that I have so this is this usual statement that I have a gap, that the intermediate particle, that the particle that you're scattering or the particle that is carrying force has a mass. If I don't have a mass, then this analysis, of course, this argument doesn't really work. I don't have this exponential suppression. But if you don't have a mass, for example, if you're talking about gravity, let's just use gravity as an example, then, so you can see that really what this is saying, what the whole point of this analysis of getting a bound on the behavior of your amplitude as S goes to infinity is really a statement that you know the long-range behavior of the interaction. When you have mass, you know that the long-range behavior is just 0 because there's a finite interaction length. If you don't have a mass, that just basically tells you that your long-range behavior is classical. Right? I mean, so that means that long-range behavior, it doesn't matter what your center of mass energy is, as long as you have large impact parameter, then it's just GR. So you can just import the information of GR in, and to control what exactly is your long-range behavior, or technically, what is the partial waves of high-spin partial wave, the behavior of your high-spin partial wave, then you can also deduce similar bounds, the S squared bound. So for gravity, we can establish an S squared bound for gravity, even though the Froissart argument doesn't work, but for gravity, because you know long range is just GR, you can use that information to come in to establish this S squared bound. Okay, so we're just going to take this as given that for either your massive or massless, that the amplitude is bounded by S squared as you go S to the infinity near the forward limit. Okay, so just take this as a given, but there's various arguments that supports that conclusion. Good, so once this is given, then you can see that now I have an equality. I have an equality where whatever is happening here, whatever that is happening here, which is controlled by these EFT coefficients here, is going to be given by whatever is given here, because they have to be equal. Right? So this means that the residue of AST star over S cubed, for example, at S equal to 0, you can see that if it's divided by S cubed at S equal to 0, that means that you're just taking two derivatives on your function S, right? That's how you pick up the degree 3 pole, right? If you take two derivatives, you see that you're going to pick up these coefficients here. These coefficients are then differentiated by taking further derivatives in T. You do further Taylor series expansion. Okay, so this gives you a residue. This gives you a residue. Let me call this residue 3, which means I'm looking at the degree 3 pole, and this will be a function of T. This will be then this will contain all the information of my GKQ. This is going to be equal to the discontinuity of the S and the T channel, U channel. And you can combine this into m squared to infinity ds, let me call this S prime cube. And since the discontinuity is just the imaginary part of your amplitude, now this discontinuity is going to be exactly what we have over there, which is just let me just call this, okay, first of all, let me just call this AL times this function here, FLD cos theta. And again, I'm summing over all L. And so I have this equality, and importantly, this, just like our previous argument, is positive. Okay, so now I have this equality. So basically, I have a relation between all of my low energy couplings with something in my high energy cosine. So cos theta, you can just replace it by cos 1 plus 2t over S prime. So this is actually a function of t. So now what you can do is you can match both sides. Yeah, so this is a function of t. This is a function of t. And t, of course, is really small. So you can do a Taylor series expansion in T. Then you have an equality between GKQ, which is your Wilson coefficient, given as a positive sum of some coefficients that you get by doing this T expansion here. Exactly, yeah, so we're doing T, right, so this is really what you get after you combine the two. Okay, so this is what we call crossing, because the discontinuity in the S channel will be the same as the discontinuity in the U channel, just through crossing. So you know that residence, so you can combine it into a function that looks something like this. Okay, and so then, what you can do is then you can just say, okay, so I have a relation between these GKQs and a positive function. And I want to see what are the range of my GKQ can be, okay? And there's an analytic way of doing this, and there's also numerical ways to doing this. So let me just show you the things that you can get from this analysis. Okay, so for example, let's say you have a four scalar amplitude. So for 4 scalar amplitude, for example, I want to look at my D6 F4 operator and D8 phi to the 4 operator. There's multiple operators that you can have depending on your tensor contraction, and they map to these three coefficients here and these 2 coefficients for 4. And then you can just do analysis, just see just using this equality, there's going to be a region because all you know is just that this is positive, okay? And since all you know is this is positive, so what the bounds that you can get is always ratios of your couplings. And so then you can get the bounds that look like this, okay? And this, I plot this because this is solved both analytically and numerically. Numerically, you use semi-definite programming to solve this. And so you can see that without knowing any precise statement about your ultraviolet, you already see that your effective field theory that you can write down actually has a finite region of possibility for your Wilson coefficients. Okay, and this is just derived from this kind of dispersion relation, where you're imposing that this is positive. I can, if you're interested, you want to know how is easy to see just from this that you get a finite region. We can talk about it probably maybe in the afternoon. But basically, it's just expanding this equation out and looking at the space that is spanned by these by arbitrary positive multiplication of the vectors that you get here, and then you get this finite space. This is for scalars. You can also do the same thing if you want to scatter gravity. So this would be constraining the UV completion of gravity. So this is looking at the space for d squared r to the 4, r cubed, normalized with the r4 coefficients. These are just various different degrees of bounds that we've put in. And so this, in the final case, basically you have the final region looks like this. And you can plot the effective field theory of string theory. And these are the Wilson coefficients of string theory plotted in here. And you'll notice that in generalities, when you draw these bounds coming from unitarity or this kind of dispersion relation, your known theories are generically very close to the boundary of the bounds that is currently being derived. So this is for gravity. This is another specific, another parameterization. So this is looking at d8 r to the 4. Since there's three couplings, independent couplings here, so we can take their ratio. So the reason I want to do this is because this has a nice feature that they're at the same derivative order. So this ratio is actually independent of cutoff because they're actually at the same order. Okay, they're at the same derivative order. So this is completely independent of cutoff. And so this is the red region that you get in the end. And again, you see all the known theories are really sitting very close to the boundary of the allowed region that you have here. This is another plot. So you can do many of these things for different couplings. So you'll notice that you might ask the following. You might ask me, why am I looking at dAr to the 4? This is very high derivative, right? I mean, if you're really an effective field theorist, you look at d8 r to the 4. This is exactly the kind of operators you don't care anything about. Right, so why am I looking at this high derivative order coupling? And the reason is because as you go to lower and lower and lower order in derivative orders, you see that there's actually one caveat that I have here when I'm doing this matching. You'll notice that there's masses pose. So when you have masses pose, so that means, for example, you have the usual graviton pole here. So what this says is that if you try to bound operators that are proportional to s squared, anything here that is proportional to s squared, there's a graviton pole that comes in. And since remember, we're doing a near forward limit expansion. We're taking t squared equal to 0. That means that this is diverging. And therefore, that means that the left-hand side, the right-hand side is also diverging in that limit. So this is actually not a converging representation. So as you go to lower and lower derivative, you start to become in danger of hitting at the same order of the graviton pole, and then you might have some problem doing this. Of course, now we also have technology to do this, and that is to instead of using your original function, you try to multiply this function by appropriate powers of t to tame this graviton pole and to get bounds. And so this is pioneered by Simon Karen-Hoyt and his collaborators. And so in that case, you can also get bounds for example, this is G3 squared, which is now related to R cube operators, as you can see upstairs. I didn't write. Oh yeah, you can. So G3 is related to the R cube operator, and you can also get bounds in the case where the couplings are now very close, on operators that are really close to what you might be interested in. So I would like to take this as an opportunity to just show how various people are using these constraints. So this is another way of trying to use these unitarity constraints. And instead of trying to use dispersion relations to give you bounds on these Wilson coefficients, so this is more what we call the primal problem. So basically what one does is to set up, you assume your S, so this is again, so this is a paper that talks about maximal SUSY, so he considers maximal SUSY. And of course, there's a low energy extension. This is the usual graviton pole, and this is the R4 corrections. So the way that this approach is that it actually constructs an ansatz for your amplitude. So it constructs an ansatz that looks like this. This rho s, rho t, and rho u is a function that looks like this. And this gives you a discontinuity in the S channel, the T channel, and U channel. So this manifests the discontinuity that you can have in S channel and T channel and U channel. Depending on how many polynomials what is the highest degree that you put in here, the ansatz become more and more complicated. But then in the end, you impose exactly the condition that I have before. You impose that the partial wave expansion is positive. And then you put constraints on your ansatz. And then you try to see what is the value you get as you increase the complexity of your ansatz, and what is the Val space that you get for this EFT coupling. And you see that as you increase n, it starts to converge. As you make the ansatz more and more complicated, the bounds on your coupling becomes more and more converged. And then the bound gives you the minimal of this. For example, for this R to the 4 operator in 10 dimension, it gives you this precise bound, the lower bound of this. And you can see, again, that both type 2a and the known theories that we have are really close to these bounds that you get from this primal primal approach. I think I will skip this. And I think I'm probably going to, let me just end a little bit early today and take questions, because this is very technical. And you can also do this not just for example, for theories where we actually don't know what the UV completion is. We want to do general. You can also do this for example, pion physics, or for example, in this case, that the people try to use this bootstrap approach to try to find or solve large N QCD. And in this case, the extra condition you get, the extra constraint besides unitarity, is that you can get some, because you already know the low-lying spectrum. So that means that on this side, you already have some information on this side, because you know, for example, the rho meson positions, the mass of the rho meson, or the coupling of the rho meson. So you can start to input information on this side. And when you input information on this side, you get, and you look at the space, and then you can see now, again, so you can find what people are generically interested in. When you carve out these space, the allowed region, you look for kinks, and generically in these kinks, it is believed that the known theories are generically close to these kinks. And so we can sharpen and sharpen and sharpen in the bound so that we can isolate to that kink, and we can do analysis on the theory that lives on the kink. Okay, so these are just a few examples of using this idea. This is something that we are doing, and maybe if there's time in the afternoon, I will discuss that in the afternoon. Okay, so it's a little bit early because I think I want to take some questions, because I think this is a little bit technical. So I'll just stop here. Thanks.
Thank you, Ethan. Okay, we have time for questions.
Yeah, considering these constraints, positivity constraints that you can impose in the UV theories, are there any UV theory that you have rolled out with this formalism?
Yes, of course. So there's various, so as I mentioned before, that there's, okay, so of course if they're ruled out, then you won't see it in a paper, right? So because these are very easy to rule things out. So there's, as I mentioned, that recently, for example, Clifford Chun, Grant Riemann, they have been proposing new amplitudes out that actually pass these tests. So I should mention that if you pass this test, this is just a necessary condition. This is not sufficient condition to tell you that your theory is actually correct. In fact, in the early string theory days, there were amplitudes that were proposed that satisfied these conditions, in which we never found a complete theory for these amplitudes. The full theory for the amplitude. And it's really a reflection that this is really just a necessary condition. And there's more conditions that you can put. So for example, what are the other conditions that you can put here? So this is really just talking about the consistency of the scattering of the lightest state, right? For example, if you assume a tree level UV completion where all of these UV states are coming in at tree level, Then at tree-level approximation, these UV states are also stable in the tree-level approximation. Then that means that you should be able to take these massive states in the UV and now start to put them on the outside. They also have to have their consistent scattering amplitude. So for example, one thing that you could do is that you could say, let's say, in the string theory example, we already know that we have the first massive state that appears at alpha prime order. That's the first level. Now you put that state, now you have a consistency equation across 3 different amplitudes. So you already have the consistency condition on 4 massless. But now you also require that the mass, the first massive state that appears here, also forms an amplitude that is also consistent to satisfy unitarity. And that the 4 massive scattering also is consistent. So right now in the EFT bootstrap community, we're just using this constraint here, where you're just using the constraint of the masses. Whatever UV state that you have here, it also must allow the consistency of these 2 amplitudes. So it will be very interesting, and indeed people are now working towards this, is to do a global constraint on this on the scattering of this of 2 lowest lying mass in the first massive, and also the 4 scattering of the first massive amplitude. And for people who are familiar with CFT, this should not be surprising, because all of these islands that are being found in the CFT bootstrap really emerge when people start to consider bootstrapping mixed operators. So if you just look at single operators, you also get these similar picture where you just have some big regions and maybe some kinks. But in order to localize on that kinks, you need to consider now mixed operators. You take operators, other operators in, and you do consistency conditions on that. So we believe that in the EFT bootstrap, this is also the case, that you had that really the next frontier will be after you do the massive bootstrap, you assume the existence of the first massive state, and you pull that massive state and you start to scatter that massive state and require everything to be consistent. And we believe that will sharpen our bounds even more.
And also, this is a very trivial question, but we are always considering these 4 amplitudes. What would happen if we consider 5 amplitudes? There will any change, or it will be the same?
Yes, that's a very good question. So actually, indeed, again, going back to this is called bespoke string amplitudes, which was recently, there's a few papers that propose these amplitudes, which are string theory-like amplitude that satisfy all the conditions that I just said, and they propose a higher point amplitude. And those theory then became later on ruled out precisely by looking at the higher point amplitude factorization, and that was ruled out. I would like to say that actually those information you can still capture in the 4-point amplitude, again, just by looking at combining these consistency. Because let me just draw a picture for you just to illustrate why this is plausible. So let's say what are the new constraints that you get from higher point amplitude? So, okay, good. So really, if you think about it, when you're doing the scattering of 4 massless particles, the constraint is really, you're constraining the exchange of this UV state between the external, right? So in some sense, we're really constraining the consistency of the coupling of your lowest lying states with the UV states. If you go to 5-point, what is the new information that you actually get by 5-point? Besides, of course, this is a more complicated function to get to constrain. The constraint is that you see that you get the UV state here. Now you get constraint where the 2 UV states, the cubic coupling of the 2 UV states with their low energy state. This vertex never appeared in your in the original 4-point amplitude, right? So you see that as you go to higher and higher and higher, what basically now you have the UV states interacting with each other. But precisely these information are now encoded if you actually start to scatter these UV states on the outside. Okay, so I would like to, of course, this is just words, and you really need to do the hard work to actually see. But I would like to believe that the higher point information you can also start to garner by just looking at the 4-point, but with these UV states on the outside.
Okay, that's all. Thank you.
Okay, thank you.
Just to again, I would like to ask you to explain the concept of when we expand in these Gegenbauer polynomials, the coefficients are positive.
Uh-huh.
Can you again explain that, just because the concept is very important?
So, yeah, so this is just because that, well, in the factorization picture, you see that it's very clear that it's positive because it's just a product of 2 3 points. Of course, it's when the 3 point on one side is the same as the 3 point on the other side. If I just talk about the partial wave expansion, then the positivity is really about the imaginary part of my partial wave. And that is just follows from the fact that, if I have a partial wave expansion, that looks like this. So I know that the imaginary part, the optical theorem tells you that the imaginary part is going to be divided by S is going to be equal to the cross-section. The cross-section is positive. So that means that I take the imaginary part on this side becomes a sum of L equals 0 to infinity. And this will be the imaginary part of AL. And this is just FL evaluated at 1. And this is just a positive coefficient. So in order for this to be always positive, this imaginary part has to be positive. So that's the usual argument.
Okay. Thank you.
More questions? So in fact, since you have this one up, so what are they getting from using this for large N QCD? I mean,
So for example, in this case, because they're considering large N, so for example, the setup will be how do you implement large N? The way that you implement large N is that you assume that your low energy is just single trace. The low energy, you don't have any double trace operators in it, so you're just bounding the single trace operator. And then you can look at the couplings. Then you can look at these the allows region for your coupling space, and you try to see if you start to see kinks in that allow region, and then you try to import the information that you have. For example, the rho meson state at a certain mass. That mass can be a parameter as well, and then you see like the space of the. So I guess this is a plot of the rho zone mass. Yes,
right.
there. Yeah, so that would be an input in your, and then you can scan the allow region that is consistent with unitarity and look for kinks.
Right.
What-
So
and
this is this is essentially showing what the rigid trajectory that includes the correct rho mass is actually, the large N limit of
Yeah.
this tier. Okay, that's good. And you mentioned something about the kink being a universal thing that people used to, when they started working on conformal bootstrap and the icing model, and they see this kink, and that's the solution. So you're saying this is a universal thing that you're seeing in
Well,
these
it's more.
kinds of...
It's not really. Okay, so basically, it's that if there's a known theory there, then as you sharpen the bounds, you sharpen the bounds, because if there's a known theory lying out there, if you try to isolate, then the known theory will show up in your bound as a kink, because that means that whenever you're doing whatever you're doing, you're shrinking the boundaries, but because there's already a solution there, so that point will not move, so it will naturally form a kink in your plots. So that's why it's natural to look for these things that start to appear as you impose more and more constraints. Because these was, of course, they will stabilize as you see that as you move, they will start to stabilize. But you see that in some region, the stabilization moves more, but in some region it doesn't move at all. So if there's some region that doesn't move at all, then it's likelihood that there's actually a solution there that's making it that there's always a solution.
I see.
Yeah.
Yes. Thank you.
And just to be clear with the terminology, I'm not sure I understand what the bootstrap is. Is it just writing some UV compilation and trying to constrain it?
It depends on how you're using so it depends on what parameters but in this case, yes, there's some UV compilation in the sense that the rho mass is one of your parameters, and you're trying to constrain the rho in the space of the rho mass that is consistent with all these unitarity equations. Of course, I can, in the previous plots, I didn't assume anything about the UV, and therefore there's no assumption about my UV model, and all I'm considering is just my EFT low energy. So really, so the point is that you have this equation that is set up for you. Mm-hmm. You can move anything that is known, you can move on the right-hand side and or left-hand side. You can do various assumptions on this equation, once you do a certain, the reason that this equation gives you non-trivial constraint generally stems from the fact that there's something that is definite positive on one side. And when there's something that is definite positive on one side, now you can start to get constraints on the parameter space that you're interested in.
But yeah, just what is bootstrapping then? Just because I'm not sure with the word.
There's a history. You have to tell the history of Bootstrap.
Oh, okay, we can discuss later, okay.
Yeah.
Okay, yeah. Then I can look it up in Wikipedia.
Yeah, you're too young to know that. Any more questions? Well, if not,
Okay,
let's
thank you
thank you, Yutin, again, and